Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. After studying about solving the equations, transcendental equation, algebraic equation, linear system of equations, and also after studying numerical differentiation, in this session we are going to talk about numerical integration. Integrating a polynomial function or a trigonometric function or a transcendental equation is easier within the given limits, but integrating a tabulated function has to be done using Newton's formula. In this session, we are going to discuss about numerical integration using trapezoidal and Simpson's rule. Also, Gaussian quadrature formula will be discussed with examples. First of all, a general quadrature formula for numerical integration is discussed, and from that trapezoidal rule and Simpson's rule will be derived. So, Newton-Cotes formula is the general quadrature formula for numerical integration. So, Newton-Cotes formula is given by integral a is equal to x naught to b is equal to xn. That is, the given interval a comma b is divided into n intervals starting with a is equal to x naught, then x1, x2, etc. up to the last point b is equal to xn. So, integral x naught to xn f of x dx is equal to h into n y naught plus n square by 2 del square y naught plus 1 by 2 n cube by 3 minus n square by 2 del cube y naught plus 11 by 6 n power 4 by 4 minus n cube plus n square del power 4 y naught plus etc. where h is equal to b minus a divided by n, where n is the number of intervals. Trapezoidal rule, Simpson's 1/3 rule and Simpson's 3/8 rule are the particular cases of Newton-Cotes formula. So, trapezoidal rule is given by integral x naught to xn f of x dx is equal to h by 2 y naught plus yn plus 2 times y1 plus y2 plus etc. up to yn minus 1. That is, in words we can say that h divided by 2, h is the length of each subinterval. Okay. So, sum of the first and last coordinates plus 2 times sum of the remaining y coordinates, where h is equal to b minus a by n and b is the upper limit and a is the lower limit and n is the number of intervals. By substituting n is equal to 1 in Newton-Cotes quadrature formula, we obtain trapezoidal rule. Next, Simpson's 1/3 and 3/8 rules. First of all, Simpson's 1/3 rule is given by the formula integral x naught to xn f of x dx is equal to h divided by 3. This h divided by 3 signifies this is Simpson's 1/3 rule. Y naught plus yn, always sum of the first and last ordinate. See, plus 2 times all even ordinates y2 plus y4 plus y6 plus y8 plus etc. plus 4 times all odd ordinates, all coordinates, that is y1 plus y3 plus y5 plus y7 plus etc. You can say that sum of first and last y coordinate plus 2 times sum of even number of coordinates plus 4 times sum of odd number of coordinates. But relating with Newton-Cotes quadrature formula, by substituting n is equal to 2 in Newton-Cotes quadrature formula, we obtain Simpson's 1/3 rule. Now, there is a condition for applying Simpson's 1/3 rule. Simpson's 1/3 rule is applicable only when the number of intervals is even, that is x naught comma x1, x1 comma x2, like that we form the number of intervals, no, that should be even, in the sense number of pairs given should be odd in number. Next, Simpson's 3/8 rule. integral x naught to xn f of x dx is equal to 3h by 8 y naught plus yn plus 2 times y indexes that are all multiples of 3 is taken into account, y3 plus y6 plus y9 plus etc. plus 3 times all the remaining coordinates is taken into account. That is 3h by 8 sum of first and last y coordinates plus 2 times sum of multiples of 3 y coordinates plus 3 times sum of the remaining. Relating with Newton-Cotes quadrature formula, by substituting n is equal to 3 in Newton-Cotes formula, we obtain Simpson's 3/8 rule. And the condition for applying Simpson's 3/8 rule is when the number of intervals n is a multiple of 3. So, number of given y coordinates or number of xy pairs are 3m plus 1. Considering truncation error in trapezoidal rule is error should be less than b minus a into h square by 12 into m, where m is the maximum value of the second derivatives, y naught double dash, y1 double dash and y2 double dash in the range a comma b, and a is the lower limit, b is the upper limit, h is the width of the interval of x values. Similarly, truncation error in Simpson's 1/3 rule is modulus of E is less than b minus a into h power 4 by 180 into m. A is lower limit, b is upper limit, h is again the width. All the other notations remains to be same. So, we can see the order of error in trapezoidal rule is h square, whereas order of error in Simpson's 1/3 rule is h power 4. Then we have Weddle's rule. Weddle's rule is given by the formula integral x naught to xn y dx is equal to 3h by 10 y naught plus yn plus 5 times y1 plus y5 plus y7 plus y11 plus etc. You can just see what are the terms which are missing, plus y2 plus y4 plus y8 plus y10 plus etc. Multiples of 3 has been taken separately, y3 plus y9 plus y15 plus etc. and multiples of 6 have been taken separately, y6 plus y12 plus y18 plus etc. Okay. The formula goes like y naught plus yn is sum of first and last ordinate. First of all, multiples of 6 is picked out. Multiples of 6 is picked out in the sense y6 plus y12 plus y18, that is multiplied with 2. Then multiples of 3 is picked out if 6 happens to be a multiple of 3, that is accounted there. Therefore, multiples of 3 except multiples of 6 have been taken into account and it is multiplied with 6. Afterwards, taking all the even numbers, if there are any multiples of 6, since already that has been accounted, except even numbers except the multiples of 6, that will be taken into account, plus 5 times remaining items, gives you Weddle's rule. And relating it with Newton-Cotes formula, we substitute n is equal to 6. When you substitute n is equal to 6 in Newton-Cotes quadrature formula, we obtain Weddle's rule. Let us see this example. Evaluate integral 0 to 6 dx divided by 1 plus x square by using first of all trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule and Weddle's rule, and also compare the result with the true result. We divide the interval 0, 6 into 6 parts, so that we can apply it for Simpson's 1/3 as well as we can apply Simpson's 3/8 rule. Okay. So, it is divided into 6 parts as 0, 1, 2, 3, 4, 5 and 6. So, the number of intervals is 0, 1, 1, 2, 2, 3, that is 6 in number. Number of intervals is 6, number of given items is 7, and f of x or y is equal to 1 by 1 plus x square. So, 1 by 1 plus 0 square is 1. Similarly, 1 by 1 plus 1 square is 0.5, 0.2, 0.1, 0.0588, 0.0385 and 0.027. Okay. So, we have formed the tabular column for calculation by trapezoidal rule, Simpson's 1/3 rule and Simpson's 3/8 rule as well as Weddle's rule. Okay. And these values stands for x0, x1, x2, x3, x4, x5 and x6, and similarly these values are y0, y1, y2, y3, y4, y5 and y6. Okay. Now, first of all, by trapezoidal rule we have the formula h by 2 integral 0 to 6 1 by 1 plus x square dx is equal to h divided by 2 sum of first and last ordinate. Sum of first and last ordinate is 1 plus 0.027 plus 2 times remaining. The remaining is 0.5 plus 0.2 plus 0.1 plus 0.0588 plus 0.0385. Okay. And h is here 1, isn't it? Okay. And the calculated value comes to be equal to 1.4108. So, integral 0 to 6 dx by 1 plus x square is 1.4108 by trapezoidal rule. Next, by Simpson's rule. By Simpson's rule, number of values should be odd, number of intervals should be even. So, number of values should be odd. Therefore, we are having 7 values. So, we can apply Simpson's 1/3 rule. By Simpson's 1/3 rule, integral 0 to 6 dx by 1 plus x square equals to h by 3 into h is here again 1. So, 1 by 3 again sum of first and last ordinate that is 1 plus 0.027 plus 2 times sum of even number of coordinates. Even number of coordinates is y2, y4. What is y2 here? y2 is 0.2, y4 is 0.0588 likewise plus 0.0588, that is all, plus 4 times odd ordinates. Odd ordinates is y1 0.5 plus 0.1 plus 0.0385. Okay. After calculating this, we get the answer as 1.3662. This is the answer by Simpson's 1/3 rule. Then, for applying Simpson's 3/8 rule, number of intervals should be a multiple of 3. Here number of intervals is 6, therefore, we can apply Simpson's 3/8 rule, and moreover number of y values is 7, that is 6 plus 1. So, multiple of 3 plus 1, therefore, we can apply Simpson's 3/8 rule, and according to Simpson's 3/8 rule equals to 3h by 8 into sum of first and last ordinate to 1 plus 1.027 plus 3 times the remaining except multiples of 3 plus 2 times multiple of 3. Multiple of 3 here is y3 and y6. y6 is accounted as last coordinate, therefore, we will have only y3. So, the remaining is 0.5 plus 0.2 plus 0.0588 plus 0.0385. Okay. And h is 1. So, 3 by 8 into these values, and it comes to be equal to 1.3571. Integral 0 to 6 dx by 1 plus x square is 1.3571. Next, by Weddell's rule, we have integral 0 to 6 dx by 1 plus x square is equal to 3h by 10. H is 1, therefore 3 by 10. First 1 plus 0.027. This is actually the first and last coordinate, plus 5 times remaining. First multiples of 6 is picked out. Multiple of 6 is not there because y6 is accounted as last coordinate, therefore multiple of 6 is not there. Then 6 into y3 only can be available and even coordinates, and then 5 times remaining. The 5 times remaining can be done afterwards, and this is for even coordinates, and 6 times. 2 times y6, y6 cannot be taken because y6 is the last coordinate, and 6 times y3, y3 is 0.1, and even coordinates, you can see the even coordinates is y2 is 0.2 and y4 0.0588, and when these 5 values are taken, when these 5 values are taken, the remaining 2 values left out is 0.5 plus 0.0385. Okay. The 2 into y6, y6 is accounted as last, therefore it will not be taken into account, and after careful calculation the value comes to be equal to 1.3735. So, this is the answer by Weddell's rule, 1.3735. Okay. Actual integration is integral 0 to 6 dx by 1 plus x square is equal to tan inverse of x within the limits x equal to 0 to x equal to 6. Tan inverse of 6 minus tan inverse of 0. Tan inverse of 0 is 0. Tan inverse of 6 value comes to be equal to 1.4056. So, you can see 1.4056 among all the values, the integral found by Weddell's rule. Among all the values by trapezoidal rule, we got the answer as 1.4108, and by Simpson's 1/3 rule we got 1.3662, and by Simpson's 3/8 rule we got the answer 1.3571, and by Weddell's rule 1.3735. So, among all the values, the value of the integrals found by Weddell's rule is nearer to the actual value. Okay. Next, we have the quadrature formula, Gaussian quadrature formula. We discussed Newton's quadrature formula, and the particular cases of Newton's quadrature formula, that is trapezoidal rule, Simpson's 1/3 rule and Simpson's 3/8 rule were discussed, and example was worked out. Next is Gaussian quadrature formula. Actually, it is derived from the general formula for evaluating the integral I is equal to integral a to b f of x dx. Okay. And the Gauss formula for a special interval -1 to 1 f of u du is equal to w1 f of u1 with the weight w2 f of u2 plus etc. wn f of un. Okay. Where ui are called abscissa and wi's are called weights. The abscissa and weights differ for each formula. Okay. So, there are actually 2n unknowns. What are the 2n unknowns? u1 to un. So, these are n unknowns, and w1 to wn, and these are n unknowns. So, totally there are 2n unknowns to be found out for evaluating the integral of the type -1 to 1 f of u du. Okay. and this particular minus 1 to 1 f of u du will be converted for general formula. Gauss-Hermite, Gauss-Legendre. Actually, Gauss-Hermite is called Gaussian 2-point formula, and Gauss 3-point formula, quadrature formula is called as Gauss-Legendre polynomials. Consider the case integral minus 1 to 1 f of x dx is equal to f of minus 1 by root 3 plus f of 1 by root 3. You can express it in the form of w1 f of u1 plus w2 into f of u2. Here the weight is w1 is equal to w2 is equal to 1 and u1 is equal to minus 0.77574 and u2 is equal to plus 0.5774. Okay. And similarly, Gaussian 3-point formula is written as 5 by 9 f of minus root of 3 by 5 plus f of root of 3 by 5 plus 8 by 9 f of 0. So, again this is expressed in the interval. Here you can have the weights w1 is equal to w2 is equal to 5 by 9 and w3 is equal to 8 by 9 and u1 is minus root of 3 by 5, u2 is plus root of 3 by 5 and u3 is 0. For the general range a comma b, let I is equal to integral a to b f of x dx, that is converted to the integration as minus 1 to 1 using the formula x is equal to b minus a by 2 into z plus b plus a by 2 into z. So, I is equal to integral a to b f of x dx. Integral a to b f of x dx becomes integral z is equal to minus 1 to 1 pi of z dz suitable for using Gaussian 2-point and 3-point quadrature formulae. Okay. We know that trapezoidal rule is given by integral x naught to xn f of x dx is equal to h by 2 sum of first and last ordinate plus 2 times remaining. You can see the weightages. So, 1 by 2 f of x naught plus f of x1 plus x2 plus etc. f of xn minus 1 plus 1 by 2 into f of xn. So, here h into summation I is equal to 0 to n wi f of xi. You can see the weights are w0, w1 etc. up to wn with the corresponding abscissa as x0, x1 etc. up to xn. For trapezoidal rule in particular, w0 is equal to 1 by 2 and wn is equal to 1 by 2, w1 to wn minus 1 is 1. So, the wi's are weights and xi's are called sampling points or abscissa. In particular, as discussed, the sampling points are x1 is equal to minus 1 by root 3, x2 is 1 by root 3 and the weights are w1, w2 is equal to 1. And for Gaussian 3-point formula, we have the weights w1, w2 is equal to 5 by 9, w3 is equal to 8 by 9 and the weights x1 is equal to minus root of 3 by 5, x2 is equal to plus root of 3 by 5 and x3 is equal to 0. Sampling point x3 is equal to 0. You can note here the sampling points in Gaussian 2-point formula are the roots of the Legendre polynomial, that is p2 of x is equal to 1 by 2 3 x square minus 1. Solve this, we get x is equal to plus or minus 1 by root 3. Similarly, the sampling points of Gaussian 3-point formula are the roots of Legendre polynomial 1 by 3 5x cube minus 3x. When you equate it to 0 and solve it, we get x is equal to plus or minus root of 3 by 5 and x equal to 0. In this session, we discussed in detail about numerical integration. We discussed various rules for evaluating an integral, that is trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule and Weddle's rule, where respective formulae were discussed. Also, we have done an example in evaluating an integral using all these all the 4 rules, that is trapezoidal rule, Simpson's 1/3, Simpson's 3/8 and Weddle's rule. Also, we discussed Gaussian formula, and from that in particular we discussed Gaussian 2-point and 3-point quadrature formula, which happen to be the zeros of Legendre polynomials and Hermite polynomials. Based on the discussion in this session, the following question may be posed. Using trapezoidal rule with h is equal to 1 by 4, evaluate the integral 0 to 1 f of x dx using the table given below. Usually we will find out the tabular column, but here in this question tabular column is directly given, so we can directly apply the formula by taking the values as x0, x1, x2, x3, x4 and f of x0 values, f of x values, f of x0, f of x1, f of x2, f of x3 and f of x4. Next, evaluate integral 0 to 2 f of x dx using Simpson's rule for the values given in the tabular column. Thank you.